Mrs. Contreras, where are you?
I
Wait,
was
no.
really tempted to click the leave meeting button.
Are we in the same place? Oh, wait,
Well,
no.
no, because I am safe inside a low orbiting satellite, and you seem like you're gonna get
Oh,
frozen in the void by Mr. Kirk. I guess I'll do this video. Let me share my screen.
oh, I don't know if they
So
could see me floating away. I was floating away, everyone. I'm not sure whose camera that was on. You want to explain why we're in space?
we're in space because it's Earth Day.
I think
But
there's some hidden
my
irony there.
well, because you can see the Earth from
Yeah.
space, right? Like, but my image is actually a screenshot from if you zoom out on Google Maps on satellite view far enough, then you get some options to go different places, including the International Space Station and the moon. You can also go to the moon.
Are you
Pretty
serious?
cool.
Just
Yeah.
like zooming out, it like eventually gives you like a pop-up notification saying, "Do you want to go to the space station?"
Yeah, it's like a sidebar thing.
Oh, cool.
It's
So
great.
that's
You
where
can
you are right
also
now.
go to, yep, but you can also visit like other planets, and then there's other like moons that have been satellite imaged in space. It's pretty cool.
Do you always see is it always the perspective of looking at Earth?
No,
No.
it's like because you know how Google Maps like lets you look at like where things are and whatever. It lets
Mm-hmm.
you also like do that, but on the moon.
Oh, so you could like turn around and look not at the Earth, but at the void of space.
I don't think it lets you do that, but like you can just like look at a map of the moon.
Okay,
Yeah,
that's cool. I might do that later.
it's pretty cool.
But did we say it's Earth Day? I forget.
It's
We've
Earth
gone.
Day.
It's Earth
Yeah, you
Day.
wrote Earth Day on your little
Yeah.
thingy thing.
Happy Earth Day.
Ooh.
Ooh. All right, let's go ahead and do some vector math. I feel like
Yeah.
vectors are important in astronomy.
Yeah, totally.
I feel like vectors are one of those things that is actively used in different STEM careers.
Mm-hmm.
I don't know how often you're busting out the law of cosines, but we might use the law of cosines today. All right,
Spoilers.
let's go ahead and get started. All right, so we're doing something called the dot product today. We're gonna leave that looming over us. This thing called the dot product. We talked about a vector product last time. The dot product is what we're gonna get to today. All right, so to define the dot product, we're gonna get in a time capsule. The thing that you're in kind of looks like a time capsule, by the way, and
Yes.
go back in time to I don't know what month, but the first semester when you guys were with Mr. Schaefer, and you did physics. So we are looking at work. Mrs. Contreras, do you remember what work? Thank you. Earth Day, nice today. Period today. Do you remember what work is defined as in physics?
It's like force multiplied by distance.
Force times distance. But it's not just force times distance. It's depending on the scenario. What is also part of that formula?
Oh, there's it like depends on the angle of like how the force is going, right? So it's like cosine theta.
Let's put a question mark there and then come back to it in a little bit. Maybe it's cosine theta. Hopefully everyone at home actually knows what it is, but if you don't, we're going to rederive it. But work is force times distance, but specifically the amount of force in the direction of the distance. Maybe that's cosine theta. Okay, so I have three scenarios here. I have a box. Who knows what's in the box? Maybe it's like Schrodinger's cat or something. We're not going to be doing that formula though. We have a box that we're applying a force to, and we're moving it a distance 10 meters. What's special about newtons and meters? Distance and force.
Does something cancel out?
Well, I guess my question is, why is this appearing in a vector lesson?
Because units are important.
Units are important.
I'm trying to read your mind. I can't
okay. Force is a vector quantity.
Okay.
Right? It has a direction and a magnitude. Right?
Yeah.
We're not applying this. You'll see in the second example, we're applying the force in a different direction, like pulling the box upward. In the first example, we're applying a force in the direction of the movement. So force is a vector quantity. Is distance a vector quantity?
No. Distance is not a vector, right?
right? How about displacement? We might be getting one of these two things I'm saying is a vector quantity and one is not. I'm not a physicist, so but you can travel a distance in different directions.
Yes.
So maybe in class I'll get people to tell me what it is because I'm sure Mr. Schaefer made a big deal about it.
Yeah, yeah.
Right? But moving in a specific direction. So in my third example, we're going to be moving not in the positive x-axis direction to the right on a sheet of paper, but we're going to be moving in a slightly upward movement. So either distance or displacement, we probably should figure out what it is a vector quantity. Can we pause the recording and find out real quick?
Sure.
We're back.
So Mr. Kirk just Googled because we needed to know. And that's what you do when you need to know.
Oh, and you grabbed me during this whole time. Okay.
So distance is, distance is vector, displacement is scalar?
No, it's the other way around. Displacement is an example of a vector quantity. Distance is an example of a scalar quantity. Distance has no direction, but displacement does. If I have an object and I move it this way and I move it this way, those are two different kind of directions. You can have a negative displacement, a positive displacement, but a distance, and actually the more I think about it, like distance is like the absolute value of a number is its distance from the origin. So distance is scalar and displacement is vector. So 10 meters here is our displacement.
Okay.
We are being displaced in the positive x-axis direction. Whereas in the third example, we're kind of going in like a upward in the y direction a little bit. Anyways, we have two vector quantities here. How much force, how much work is being done on the box if you apply a 50 Newton force to move it 10 meters?
500.
500, right? 50 Newtons times 10 meters equals 500. Do you remember the units? I know it. So we're not going to have to Google this.
Newton meters.
Newton meters is correct, but also joules. Joules is the single term, but Newton meters is often used. Newton pounds, yeah, not Newton pounds. Man, don't ask a math teacher to teach you physics. Anyways, hopefully this is all review. Foot pounds.
Totally foot pounds.
Yeah, foot pounds. Okay. So scenario number 2, I'm going to give you an arbitrary angle. Let's go with 45 degrees, which is the same as pi over 4 radians. All right. We are looking at the force in the direction of the displacement. So we're being displaced 10 meters. But how much force is in that direction? Because some of our force is up and some of our force is in the direction of our movement. Some is perpendicular, normal, if you remember that word from physics, and some is parallel. What is that parallel distance?
Parallel force. 50?
Less than 50. Okay. So this is 50. We have a 45 degree.
Do we need root 2 over 2?
This would be like if we're doing similar triangles, we would have a triangle that is 1, 1, root 2.
Okay.
I'm just thinking, SOHCAHTOA, the cosine of 45 is equal to the thing that we want, the force, and I'm actually going to write F with a subscript of X. That force divided by 50 is equal to cosine 45. Cosine 45 is root 2 over 2.
Mm-hmm.
So root 2 over 2. So it's going to be 50 times root 2 over 2.
So is that 25 root 2?
Yeah, 25 root 2.
That
25 root 2 over 2, 10 meters. I'm going to get rid of the meters. We're going to be Newton meters. And that is going to be 250 times root 2. Right? We are doing less work here. Or are we doing more work? Man, I'm not a physics person. Doesn't matter. Let's keep going.
Root 2 is less than 2.
Mm-hmm.
So it's less than 250 times 2.
Yeah,
So it's
yeah,
less. And that makes sense, right?
yeah, because there's less force going in the direction of the displacement.
Mhm.
Cool. All right, so we can establish work there. All right, keep it. I love that. You got rid of that, so we have the space.
Yeah, I guess so. I'll make it really small.
I like that. Okay, cool. All right, so new situation. We have a force. We don't know what it is. We have an angle. We don't know what it is. And we have a displacement. We don't know what it is.
So we're trying to generalize what we did before then, huh?
Yeah. And our displacement is now in a new direction. So how much work is being done? What's our displacement?
Cosine of theta times the force, right?
Well, actually, let me do this. We're going to move this box this far. That's our displacement.
Okay.
With that said, what is our displacement in general? It's just D, right?
D?
The displacement
Okay.
is the number I've given you. That's how far we're going.
All right.
Now, the question you were about to answer is how much force is in the direction of D?
Okay. And so that depends on the theta.
Mm-hmm.
And it's scaled from our actual, the force that's being exerted in that direction. So cosine theta times F.
Yeah, force times cosine theta. And then just for kicks, the normal is 4 sine theta, right? That comes up in torque. When you have some sort of arm and you're moving it, the sine theta is what you can think of when you're thinking of torque force. So what is the force times the displacement in the direction of the displacement? What is that going to be?
F cosine theta times D.
F cosine theta times D. So I'm going to do F D cosine theta. Same thing, right?
Yeah.
Boom.
It's commutative property of multiplication.
Boom. All right, so rewind. Title of the lesson, the dot product. This is the definition of the dot product. Force is a vector. Displacement is a vector. Two vectors have an angle between them. If you are given a vector, u, and a second vector, v, the dot product, and we put a little dot, is the magnitude, and actually, since these are vectors, I should put the magnitude bars around them. The magnitude of the first vector times the magnitude of the second vector times cosine theta. So last time we talked about multiplying vectors. Here's another way to multiply vectors. Take the magnitude of u, the magnitude of v, and then also multiply by the cosine of theta. Why is this a valid way to multiply two vectors? Because it has physical application. This is another way to define the product of two vectors. Work. Let's use it. Let me scroll down. I have a vector 4, 1. I have a vector 2, 5. I want to find this product, u times v. Or u times v, it's already written on the page, but I'm going to write it again. U, v, cosine theta. Where angle is the, theta is the angle between u and v. Let's figure this out. So what are you thinking?
First, I'm going to label these.
Cool.
So I can visually see what's going on. Well,
all right. And I totally agree that the upper one is 2, 5 and the lower one is 4, 1. Yeah.
Sweet. Thank you.
Yeah.
So how should we just like find some values?
Yeah, let's just find some values. What is the mag u?
Mag u.
When I say mag u, I mean the magnitude of u, but I'm lazy and I shorten a word that doesn't really need to be shortened.
And then you had to explain it. And so it's like even longer. All right. That's what root 16 plus 1. So that's root 17.
Did you write it?
No.
Oh.
I'm
So
writing it
root.
now.
Oh, you're writing it now? Okay. I'm sitting there like, when's it going to drop? You had the inflection in your voice that implied writing in my mind.
All right.
Sweet. Okay, root
I will
17.
write out all of it. Okay.
Huh?
And then what's the magnitude of V? Mag V. What's that? I'm writing now. Root.
Sweet. I appreciate the
plus,
clarification.
25. And so that's what, root 29?
Sweet. All right, so we have the magnitude of u and the magnitude of v. Now, if we want to find the product of these two vectors, we're not just going to multiply those two numbers because there's this other thing, cosine theta. Right? 4, 1 can represent, by the way, a force. Maybe it's a force of 17 newtons. 2, 5 can represent a displacement. It's a displacement of root. Oh, no, I said that wrong. Root 17 is the displacement in the direction of u. We're trying to find the work being done by u or v onto u or u onto v. They're the same thing. It's commutative. All right, we need the angle theta. Or specifically, we need cosine theta. We could find theta, but we could also find cosine theta. This is almost something. And also my other hint is we are still in the triangle unit, technically.
So it's almost a triangle?
I'm sorry that I'm making it so easy. I want to.
I like the softballs. It's nice.
It's like, here you go.
I'm on my second cup of coffee today.
Oh man, look at this. Is there an issue with 32 ounces of coffee? Anyways, how can I complete my u and my v so I have a triangle?
Connect them.
Yeah, connect them. I'm going to connect them. I'm going to connect them this way. I'm actually going to get the straight line tool. Boom. Shabbat.
Lovely.
I just drew a blue vector. Can you tell me what that blue vector is?
Well, it's not the sum of u plus v.
It's not the sum of u plus v, but what is this? What is the sum of what other two things? Softball.
Sum.
We have 3 vectors here, and 2 of them sum to one of them.
So u plus the blue one equals v.
Yeah, let's call it B for blue.
All right.
U
not G
plus.
for Grover.
Do you want it? I'm not going to do G because the green is being used. U plus B equals V. I'm going to rewrite that. V minus, let me make sure I get this right. I need to write it again. U plus V, B equals V. If I subtract the U, B is equal to V minus U. What is V minus U?
V plus negative u.
True, but like we have numbers.
Oh, -2, 4.
Sweet, cool. What's the magnitude? What's mag V minus U?
Oh my gosh! Please don't make this a thing. Root.
I swear I was taught mag U and mag V in college or something. Am I the only one?
I don't know.
Okay.
I might have learned it, but then forgot it because that happens.
Yeah.
Was that root 4 plus 16, so root 20?
Sweet. All right, root 20. All right, so back to my original question. What is theta? Or if you'd rather, what is cosine theta?
Maybe we can use the law of cosines to help us out because we have sides.
Also, I've been hinting law of cosines since like the beginning of time. Let's do it. We got 3 sides. Oh, we got since the bit. We have 3 sides. They're all square rooted, which is actually quite nice because we're going to square them in the law of cosines. I'm going to call this B just for the sake of it. What law of cosines do you want to use?
because we want to have cosine theta come out of it, right?
Mm-hmm.
So then we need to deal with b.
So root 20 squared is equal to root
17, 29. Oh,
17,
do that too. That's responsible.
29 minus root 7. Oh, I was about to forget it.
2.
I'm telling you, man, it's the most forgotten thing in all of math.
Maybe we need a song.
We need a song. Music people out there, get us a song. And theta.
Maybe you should assign a song project.
I should assign another R project, but highly encourage songs to be made. I don't want to make people do music that don't do music.
But you'd be surprised how much music can come out of people.
No, you're right.
When
You know,
challenged.
I need to be less pessimistic about musicianship. Let's proceed though. We got 20 square roots, and the square don't truly cancel, but in this case, since 20 is positive, they do. Right? No absolute value needed. 29 minus 2. I'm going to combine those. 17. No, I'm not. I'm going to keep them separate.
Okay.
Cosine theta. Cool. Hey, do you notice something? What are we looking for?
We're just looking for cosine theta by itself, right?
Right. So do we actually need to find theta?
No.
No.
We just need cosine theta.
Yeah, let's like not do the arc cosine later. Let's just like solve for cosine theta.
Because then we would introduce what, float point error? Something
Yeah.
like that.
Float point error. 20, 17. Let's do some subtraction, division. I'm going to do this. We're going to subtract the 17 and the 29. But then we're going to divide by the -2. So that's going to be equal, and we're going to divide by -2 root 17 root 29 equals cosine theta. Is that okay with you? If we do that big jump?
So you pushed cosine to the left. Okay, sure.
Yeah, I pushed the whole cosine term to the left. I moved the 20 to the right, and then I divided by +2 root 17 root 29.
Cool. I was going to cancel out the 20s, but yeah, that's fine. Right, because 20 and 29, so you just like make it 9.
So 9 and 17 is 20. What is that?
26.
26. And then the 2 and the 26 become a 13.
Mhm.
Let's leave it like that. Let's leave it like that.
Yeah.
All right, so we have root 17, root 29 cosine theta. The work being done, the dot product between u and v. Let me fill that dot in. This new type of multiplying vectors is root 17, root 29 times cosine theta, which we've just established is, things are about to cancel. 13, root 17, root 29. Oh, bam. Where's the Star Wars?
Oh my gosh.
Use the force. You, Mrs. Contreras, use the force on this one. 13. 13. And if these were forces, 17 newtons. No, U is our, it doesn't really matter. Let's go ahead and say root 17 is our displacement, and 29 is our displacement. So that's going to be meters. This is going to be newtons. We get Newton meters or we get joules. 13 joules of work has been done.
Sweet.
Right? Vector math is used very often in physics and engineering because so often you need two values to be represented in one object. Let's do that in general.
Okay.
I know it was a little bit exhausting. I think with the practice problem with numbers, it should be pretty straightforward in general. Okay.
Okay. We need to make a triangle.
Which vector do you want to call what?
Let's just stick with what we had before, where u is, yep, and then v is the other.
And then this was v minus u. Let's call it v minus u.
All right.
All right. And we're solving for cosine theta here.
Mm-hmm.
U dot v is equal to u v cosine theta. So the question is, what is cosine theta? Right. Hopefully we get some canceling like we did here. All right. That should be a big not red flag, green flag. Woo! Canceling hopefully will appear. Let's do it.
So u minus v is going to be x2 minus, sorry, v minus u is x2 minus x1, comma, y2 minus y1, which looks suspiciously kind of like a slope formula. But okay. And then we have.
Let me get this, x1, y1.
So our magnitude on. Oh, you're at school.
I am at school.
It's like, what?
X2, y2, okay.
Okay. So then magnitude of u is root x1 squared plus y1 squared. And then magnitude of v is the same thing, but with twos.
Boom. And then the magnitude of v minus u is going to be relevant to us. What is that?
That's going to be square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared.
Okay.
It's suspiciously like a distance formula.
Okay, let's throw it into the law of cosines.
Okay, so then what you just wrote squared.
Is it okay if I just do that?
Yes.
Right, because it's square rooted, but then I square it.
Mm-hmm.
Boop, boop,
that
boop,
equals boop. X1 squared plus y1 squared plus x2 squared plus y2 squared.
I'm catch up.
That's cool. You good?
X1, so this might get a little long. X1 squared plus y1 squared, square rooted squared, plus x2 squared plus y2 squared, square rooted squared, minus 2. I'm not going to forget it. Square root x1 squared plus y1 squared times x2 squared plus y2 squared times the cosine of theta. That's the thing we want.
Beautiful.
All right, there's a lot going on there, but you know some Jedi are about to appear and then eliminate some stuff. Because look at all these squares that are appearing everywhere.
Yeah, it's gotta go.
Can you expand x2 minus x1 for me?
Yeah, x2 minus x1 quantity squared. That's a x2 squared. Oh, you got it.
Oh, you writing it?
No, you got it.
Okay.
And then minus what? 2x1 x2.
Sweet. I was jokingly forgetting the 2x1 x2, but you did not.
That's good.
All right, then we have plus y2 squared plus y1 squared minus 2y1 y2.
Lovely.
Sweet. And then all of the stuff above again.
Yep. Are you going to write it again, or would you like me to copy it?
You want to do a little copy paste action?
Yeah, because you can do like the screenshot thing and then just like.
It's going to go off the page. So you're going to have to make smaller, but I think that's okay.
Just a little bit smaller.
Yeah.
Like that.
All right, Jedi Contreras, you do the honors.
All right.
Is that how you refer to a Jedi? Jedi.
Wouldn't it be like
Anakin?
Master
Contreras.
Yeah.
Will you do the honors?
Indeed. Where'd it go?
We're gonna get hit with one big lightsaber slash at the end because none of it's dropped. Bam! Woo. All right, lots have canceled. So we have, I'm gonna rewrite this in orange, negative 2x1 x2 minus or plus negative 2 y1 y2 is equal to -2, the square root of x1 squared plus y1 squared, the square root of x2 squared plus y2 squared cosine theta.
That. And we just want cosine theta.
So cosine theta is equal to.
Oh, we can cancel out those -2s.
Vizhoo, vizhoo, vizhoo.
And just make it a plus.
Awesome. Oh, you just made them pluses. That's kind of smarter.
No, like you just make this one a plus. Cancel everything else out.
But the 2's go away, you're right. So
Yeah,
we
let's
got,
just go away.
we have, let me actually not skip any steps. We have x1, x2 plus y1, y2 is equal to the square root cosine theta. X squared plus y squared, x2 squared plus y2 squared.
Cool.
Sweet. And then it's getting a little bit tight here, but cosine theta is equal to x1, x2 plus y1, y2 divided by
Can
square.
we be lazy and rewrite that as the magnitude of u times the magnitude of v?
Absolutely.
All right, cool.
All right. So now we have cosine theta. And let me just go. We have cosine theta, and we want u dot v is how we say that phonetically. U dot v, which is uv cosine theta. So u dot v is equal to u v cosine theta x1, x2 plus y1, y2 all over u v. Okay, we get that canceling.
It's gonna cancel.
Wait a second. U dot v is just equal to x1, x2 plus y1, y2.
That looks hauntingly familiar.
That looks hauntingly familiar. Where have you seen that before?
I think it was in the previous hilarious YouTube video.
With thousands and thousands of views and 5-star lots of likes, no dislikes. There you go. So that thing that we talked about last time is the thing that we're talking about this time the whole time. That thing that we talked about last time was the dot product.
This whole time.
Which told you what? What was
product?
It told you the product, but yesterday when I gave you 2 vectors and you did this operation, what was it enlightening you to?
If 2 vectors are perpendicular or not. Because if they were perpendicular, then it would come out to be 0.
0. And then what's the angle between 2 perpendicular vectors?
90 degrees.
90 degrees. If I scroll up, here's how the dot product is defined. What happens when you plug in 90?
0.
Cosine 90, 0. Boom. U dot v is equal to 2 different things. It's defined to be the magnitude of u times the magnitude of v, a product, times the cosine of the angle between them, work. But it's also, if dealing with vectors, just the product of the x and the y, the 2 x's plus the product of the 2 y's. Very easy to calculate work when doing physics with vectors. I would argue much easier than what it was when everyone was with Mr. Schaefer and calculating work the old-fashioned way, finding the angle between them. Boom. I have a u vector. It's my my force. I have a v vector. It's my displacement. 6.2, -1.8, respectively. How much work is u doing on an object moving in the direction of v, the length of v?
So this is where we actually need to find theta. So
or just we could find theta, but we have this new formula.
Like we can't just solve for cosine theta. We have to actually get the theta. Like we have to use arc cosine, right?
If we want the angle between, it says find the angle between them. I was reading the problem wrong. You actually read the problem. I was making up a new problem in my head. How much work is you doing on v, an object in the direction of v? But if we need the angle, you're right.
Cool. But we need to do the dot product anyway.
We do. So cosine theta is equal to u dot v divided by mag u mag v. That's that thing up here.
Yep.
I've rewritten x1, x2, y1, y2 as u dot v.
Cool.
What is U dot V.
-6 plus 16, so 10.
10. Magnitude U. I said the whole word for you.
Root 40.
Magnitude V.
Root 65. Magnitude gives me just like a half second longer to think about it, and I like that.
Nice. I hear you. All right, and then I got a calculator here. Let's find out what this angle is. Arc cosine of 10 divided by parentheses square root 40 square root 65 close parentheses.
Did you close your original parentheses on the root 40? Okay. Because like
Yeah.
I would be lazy.
I'm pretending. I know. Just look at the earth. You'll see the answer. I got 78 degrees, 78.690. Boom. That's the angle between them. But the work is 10. The work that an object of force 6.2 on an object in the direction and length of -1/8 is 10 joules. Just keeping in mind that the vectors are used in physics a lot. So let's place ourselves in a physicist's shoes to some degree. No pun intended. Okay. We have one last thing to do in this video. Let's knock it out so the video doesn't get too long. It's starting to get a little long, but oh well. We got a little bit more to do. Let's do it. We are going to explore a vector called the projection of U onto V. I always say it out loud when I'm solving for it. And as I say it, I write it. The projection of U onto V. I'm going to write it out to you. The projection of U onto V. Right? Saying it out loud, writing it down really helps me understand what this weird set of letters is actually saying. V is like our basis. It's like the base. It is just like a logarithm. It is the base. And we are projecting U onto it. Do you know what that vector is going to be visually? Can you draw for me?
Is it going to be on V?
It's going to be on V. V is like our base. And we're taking the U and we're going to like cast a shadow onto V. There it is.
Try to make it slightly.
Another way to think about it, since we're doing so much physics, is it's the amount. It is the amount of U that is in the direction of V. We can decompose vectors into. I'm going to add a little bit. Let me actually not make it purple, orange, because that might imply that the orange one was the projection. It's not. Right?
Mm-hmm.
Can you actually make your line orange?
Absolutely.
So that everyone knows that that is the projection?
I was totally just about to do that. That's hilarious.
Sweet. Right, so challenge to everyone at home. We're about to figure out a formula for the projection of U onto V. But once the orange vector appears, try to think of a way to calculate that vector, that orange vector there.
There it is.
That is what we're going to figure out. That vector, given the vector U and the vector V. Right. Actually, the length of V isn't going to matter. Doesn't matter how long V is or how short V is. V could be shorter than this could be V. Okay. We're still looking at the amount of U that is in the direction of V is what we're trying to figure out here. That orange vector. This is called a normal vector. Sometimes it's useful, but we are trying to find this orange vector. Projection of U onto V. I always write the U before the V. I say it out loud as I write it. Okay, let's figure out what this thing is. Let's give variables to U and V.
Like x1, x2.
Yeah. Do you want to use x1, x2, or do you want to use
like AB?
AB. What are you feeling?
AB.
AB. And then maybe CD.
Sure.
Right. So that is the premise here. We are given A, B, C, and D. Those are numbers, not variables, numbers. And our job is to find out what the projection of U onto V is. All right. Thoughts? We need a vector quantity, by the way.
Mhm. So I feel like we need some scalar, the proper scalar, to multiply by v.
Mm-hmm.
So how much do we scale it down? I think it
So scaling
depends
it
on
down.
what that angle is.
Can I give you a hint?
Sure.
Instead of scaling down v, is there another vector that is parallel to v that might be easier to deal with? We'll come back to that one. Do you know
Okay.
how, I don't care about the direction. Do you know
Okay.
how long projection u onto v is?
It's going to be cosine of theta is going to be the projection over the magnitude of the projection over the magnitude of u. So then the projection magnitude is going to be the magnitude of u times cosine of theta.
Magnitude u cosine theta. Sweet. We have the length now. Right, just to make it clear what was done here. Let me write this. Cosine theta is equal to adjacent over opposite projection of u onto v divided by
hypotenuse.
Adjacent over hypotenuse. Thank you. Yeah, not cotangent. Cosine. All right, so this is the formula that I believe you used, and then you just did a little bit of flip-flopping, and you got this thing. Cool. We have the magnitude now. Our goal is to get the vector. What vector could we multiply by the magnitude to get the vector we want?
I'm confused.
Let me just draw a little quarter circle here. This quarter circle is going to be a unit circle.
So then that's going to give us.
What's the magnitude of this magenta, this maroon, whatever it is, vector I just drew?
1.
It's 1. If I have a vector that's length 1 in a specific direction, what can I multiply it by to get to my orange vector?
The projection?
Yeah, the length of the projection. 1 times u cosine theta is going to give me a vector that is the length u cosine theta. And if I have a vector that is 1 unit length in the direction of v, I'm now going to have a vector that is the length I want and the direction I want. So let's call this like M for magenta. What is M? Or how about this? Its length is 1. It's in the direction of v. Let's use what we learned last time.
Oh, it's our unit vector v.
Yeah, unit. If we get a vector in the direction of v that is a unit length, so v hat, we multiply by u cosine theta, we get that projection vector. What is v hat in terms of things that we know?
That's v, which is cd, over root c plus c squared plus d squared.
Yeah, so it's c comma d divided by the square root of c squared plus d squared. Sweet. All right, so let's construct this vector. The projection of u onto v is, notice I don't have the bars anymore, the vertical bars. We are getting a vector, not a magnitude. It is going to be u cosine theta times c d over, and I'm not going to write cd, I'm just going to write v over mag v. All right, what are your thoughts? Let me read this in maybe in a neater way. U V over V cosine theta. Do we know theta? The problem, I didn't really make it explicit, but given this problem, we're given two vectors. We're given AB and we're given CD, and we're looking for the projection of U onto V. I don't know what the angle is. I could find out what the angle is, but I don't currently know what it is. So can you think of a way to get rid of this cosine theta?
Well, can we use the dot product?
Yeah, what is cosine theta?
Cosine theta is our dot product divided by, yep, right there, magnitude of U times the magnitude of V.
So let's go ahead and rewrite this as U vector V divided by vector, the magnitude of vector V times U dot V over U V. Things cancel, right?
Mhm.
We have the U's cancel. The magnitude of V is a number, so I can actually square that. The top is U dot V, and we multiply by V. This is that number that you referenced earlier. That is the special number that takes your vector V and scales it down. Right?
Yeah.
The projection of U onto V is equal to that thing. That's the number. To get to it, we scaled down to 1, and then we scaled up to projection U onto V. But U dot V over V squared times the vector V is the formula for the projection of U onto V.
Sweet.
Let's use it to like maybe cement it in our brains a little bit more. I know that that's a lot of information.
Can you
Review?
erase that circle?
I can.
Cool.
All right, cool. We vectors U, vector V. We want to find the projection of U onto V.
So we need U dot V. And that's going to be 14 minus 12, so 2.
So you have
all right, what I'm saying is
14
like,
minus
okay.
12. So that's 2. I'm just going to write 2. Actually, no, I'm not. I'm going to write 2 now on the second line.
Okay.
Boom.
And then the magnitude of V squared is going to be 49 plus 9.
58 square rooted squared. So just 58.
And V is still going to be V.
Yeah.
True.
1/29.
Yeah.
Yeah. And then V, we have V, 7/3.
7/3.
Boom.
So we could also write it as Langle with the 7/29.
They don't simplify nicely. The projection of U onto V is equal to 7/29, 3/29. I'm going to draw this real quick. We have 2, -4. 2, -4. It's kind of like this vector. It's a little sketch. 7, 3. And we're projecting. Oh, this kind of makes sense. 7, 3 is going to look like kind of like that. Yeah. And we're going to project this vector onto this one. So it's going to be. Let me zoom in real quick.
Wow.
That is intense. We have this vector U, and it's being projected onto V. We just got this little blue vector, which we claim is 7/29, 3/29. That's about right. Answers aren't always going to be this small, but in this case, they're close to being perpendicular. So the projection is going to be very small.
Sweet.
Sweet. One last thing before we close this video out. So we just figured out the formula for the projection of a vector onto another. Let's see. Ooh, 17,190 teachers actively using Kami right now. Kami. But I want to expand the magnitude of V squared real quick. So given a vector v, let's call it x, y. The magnitude of v squared is x squared plus y squared squared. Follow me so far?
Mhm.
So the squares go away. And I'm actually going to break up the x's and the y's. Follow me so far?
Mhm.
Right. This is v dot v.
Mm.
Right? The magnitude of a vector squared is just it dotted with itself. So my favorite formula for the projection of vectors, so the projection of u onto v is u dot v over v dot v, v. U dot v over v dot v, v. So lots of v's and u. V is very important. The thing that you're projecting onto is very important. And then u is the thing that determines that scalar that takes you from v down to or up to where you should be. Boom. So there's a formula, but some people prefer the one that we came up with earlier. Where is it? U dot v over v squared times v.
Magnitude v squared.
Yeah, mag v squared.
Mag v squared.
I like the u dot v over v dot vv though. I actually like saying that. That's like that has potential for a song.
It does. I was feeling it.
All right, there you go. Boom.
Cool.
Projections. Let me scroll back up. Here we are. We started with work, and we defined a lot of stuff in this video. So there's a fair amount of practice that is due. Let me go ahead and stop sharing. Any words of wisdom?
Do your part for climate change, slowing down, stopping, reversing. Do your part.
Man, what a goal to reverse it. That's the goal. Because we are doing damage and we need to stop it. You have to slow it down and stop it before you reverse it, but that's calculus.
That's calculus.
You can't reverse it unless you do the other two things first.
Yep.
All right.
You, Mr. Kirk.
My word. I'm not going to give words of wisdom today. I'm going to give a charge. Do something for the planet today. When you're watching this, it's not Earth Day. This was recorded on Earth Day, but you don't have to wait for Earth Day to do something for the Earth. So today, watching this video, when it's done, close it, go outside and do something for the Earth. I don't know what that is. Maybe it's plant a tree. Maybe it's pick up some trash that you see on the ground. I don't know. That's my charge, not my words of wisdom today.
Sounds good.
Cool. Want to close it out?
Sure.